Hello everyone, welcome to our first video. Today we're going to be talking about complex numbers, which if you've never heard of complex numbers before, we're really talking about imaginary numbers. If you've seen those before, then you might know what I'm talking about. But if not, don't worry. This is kind of a basic introduction to them. But if you've ever seen the letter I representing a number in math, then you probably know what I'm talking about. But again, if not, don't worry about it. It's fine. We'll kind of start from the beginning. So, let's see. First things first. I guess in this section, the book doesn't really cover exactly what I is, but maybe just as a reminder, I'll start at the top here. I, by definition, we say I is the square root of -1. And that could come in handy down the road, later on in this section we might need that. But that would mean, if you kind of think about it, let's see, if I were to raise I to the second power, for example, let's try that. Then that would mean that, oops, I don't want that, I want this, here we go. That I to the second power, I squared is, well, if you think about it, the square root and the square would cancel each other here. Because they're opposite operations, so you'd just be left with the number that's inside the root, -1. So yeah, like I said, that might come in handy later on in this section. We might as well keep that in mind. Let's see, so I'll kind of highlight this information. The I is the square root of -1, and then I squared is -1. Okay, but let's just jump right into this here. So we have this idea of, why do we study complex numbers or imaginary numbers? That's a very good question. I always wondered that as a student too, but I was kind of too shy to ask questions, or I didn't want the teacher to make fun of me for asking stupid questions. I don't know. Something like that. But it's not a stupid question. It's just, I is not a real number. If you remember from previous classes, if you've studied square roots before, you can't put a negative number in a square root. It doesn't make sense. So this is a number that doesn't really exist, that we're aware of. But kind of as it says in this little box here, it says, why do we need to study something if it's imaginary? It says, the numbers that we study in this section were given the name imaginary, but that was back when, this was a long time ago. A lot of math was, someone came up with it a long, long time ago. But when they came up with this, they had no idea that there were actual uses in real life for imaginary numbers. So I guess, the name still kind of makes sense, but the imaginary numbers actually help. I've heard people say it a lot in physics. A lot of physics applications, imaginary numbers make things easier. So I think you have to be really deep in physics or computer science to really, really see it. So, and I just majored in math, so I haven't really seen that much physics or computer science, but I take their word for it. I have been assured that you do use it. But let's see. But complex numbers, they don't really even do much of an intro here, but let me see, just off to the side. You don't have to write this down if you don't want, but it might help, especially if you're not really familiar with these guys. Complex numbers, all they are is numbers of the form a plus bi, where the I is what we've defined, I is the square root of -1, but a and b, where a and b are real numbers. So, if you want an example, something like 1 plus 5i, that's an example of a complex number. I guess you call it complex because it's kind of complicated in that there's a real part. The 1 is just a regular real number that we're used to, plus an imaginary part. The 5i is the imaginary part. But the numbers 1 and 5, they could be other things. It could be a square root, for example. Like I could put the square root of 7 or something like that, and then minus 1i or something like that. That's also a complex number, so it doesn't have to be a whole number. You could have fractions, so something like 3/4, that's fine, plus maybe like a 5th root. You wouldn't see that. That's just kind of an example, just to show that there's a lot of things that are considered complex numbers. What, a 5th root of 2? I don't know. Something like that. And then there are also, if you just have a real number, for example, I don't know, there's all kinds of them, right? But let's try 9. So 9 is actually a complex number, even though I don't see an I, and it's because 9 is equal to 9 plus 0i, So I guess technically if you write it that way, 9 plus 0i, that still is a complex number. But we're just used to calling it 9, but in disguise, he's also a complex number. And then there's also the ones that are completely imaginary, so just something like negative 10i. So that one doesn't have a real portion to it, it just has the complex portion. But you could, again, similarly to the last part, you could think of it as 0 minus 10i. And that technically kind of looks more like a plus bi, sort of. Yeah. So that's kind of the idea, but those are the guys we're going to be dealing with in this whole section. We're going to learn how to add complex numbers, subtract them, multiply them, divide them. So I apologize if you've already seen this in a previous class. You're probably going to be a little bit bored. But hey, you know, when you're bored in math, that usually means you're doing good because you understand the material, right? So it's kind of, you know, it's a double-edged sword. It's got good and bad. But okay, we might as well try jumping into one of these examples. And if you've never seen this before, you might guess on how to do these. You know, like here in example 1 here, I just want you to add these two complex numbers. Here's one of them, 5 minus 2i, and here's the other guy, 3 plus 3i. So you might think, well, maybe this is more complicated than I'm thinking of, but what I'm thinking is I'm just going to add the like terms. So there's a 5, there's a 2i, okay, or I guess you could think negative 2i, and there's a 3 and a 3i. And I'm kind of just rewriting it without the parentheses because there's not really any reason for those parentheses, you know? It's not like there's something to distribute, like here, this plus. I guess you can think of distributing a plus onto the 3 and the 3i, but that's not going to do much, right? If it was a subtraction sign, that'd be different, but we'll see that in the future. But yeah, it's kind of exactly what you would think. We got kind of like terms here. The 5 and the 3, they're the real portions because they don't have an I attached. And then I have sort of my imaginary numbers here, the negative 2i and the 3i. So those guys are like terms. I can go ahead and combine those. Let's see. So the real parts, I got 5 and 3. Those add up to 8. Then I have the imaginary parts, negative 2i and 3i. They're just, you could write, I guess, 1i at first, but as you've seen with variables, like in algebra, you don't want to have a 1 in front of your variable. It's not simplified all the way. So I'm just going to write I instead of 1i. And that'll be it. So it kind of seems silly, but I guess what the big goal here is when you add, subtract, multiply, and divide complex numbers, you want to make sure your answer is a complex number. So and right now we're adding, but that goes for all operations. So I'm going to try to keep that in mind. Answer must be in the form a plus bi, and that's probably something important to keep in mind, especially when you're doing your homework. Because if you're doing online homework especially, they really want your answer, you know, in a certain form. And when you enter it, you won't have to write the real portion. So here I would write, type in 8 and then plus and then the I. So if you were to write it backwards, for example, I plus 8, it's the right answer, but it's not the form they want. They want to see the real part, 8, and then the imaginary part, I. So keep that in mind when we do the rest of these problems. So this part over here, this next other part, I guess, example 1, part A, we have a very similar thing going on. There's just two complex numbers. There's a plus sign in between them, so there's no real need to have those parentheses, you know, and there's nothing to distribute, so I'm just going to rewrite it with no parentheses. And then I'll determine what are the like terms here. The 7 and the 1 look like they're like terms. They'll add up to 8. And then I have 2i and negative 4i. Those add up to, negative 2i. And that's it. So I kind of, as a check in my mind, I say, okay, is that in the right form? Do I have the real and then the imaginary on the right side of the real? Yes, I do, because 8 is the real, 2i is the imaginary. So that's a perfectly fine answer, no problem there. Okay, well, we can move on now. Example 1b, now they want us to subtract. So that's a little more work, I guess, because now if we try to remove the parentheses to determine what the like terms are and all that, we're going to need to distribute the subtraction sign. So I'm going to keep that in mind. This little subtraction guy here that you see, I'm going to need to distribute it onto the 12 and onto the negative 4. But the first complex number, the leftmost one, 2 plus 6i, there's no need to really, there's nothing there to distribute, you know, because there's nothing to the left of that number. Okay, but I will distribute the negative or the subtraction sign onto the 12, okay, making it a subtract 12 or negative 12. But then when that negative sign goes onto the negative 4i, or the subtraction sign goes to the negative 4i, two negatives make a positive, so it'll become a plus 4i. But at this point, it looks a lot like the previous two examples. We could just kind of determine the like terms. We got 2 and negative 12 make negative 10. And then we have 6i and 4i make positive 10i. And that's it. And like I said, you just want to make sure that the imaginary portion is on the right side. So the 10i should be on the right, and the negative 10, the real part, should be on the left. So I think it looks good. All right, let's try the next one. This one should be similar. It's just, you know, here's another one to practice. This negative, or sorry, the subtraction sign, I'm going to distribute onto the 5 and the negative 7i. So let's see. I have the 3 plus 2i, which doesn't change, but the 5 becomes negative, and the negative 7i now becomes positive. All right, now that I've done that, I'm just going to grab the like terms. We have 3 minus 5 makes negative 2, and then we have 2i plus 7i. They add up to 9i. There we go, and that looks good. And I know you've probably seen, I don't know, some math books, if they end an answer in a negative in the front, they might switch the terms. You know, you might, especially like in algebra, you might have seen if you end with something like negative 2 plus 9x, or something, I don't know, any kind of variable. A lot of times they'll switch them because it's just kind of more pleasing to the eye to have the negative on the right side instead of the left. And that was I guess before when we didn't really care how the answer looked. We just wanted it to look pretty. But now since we want it to be in the form a plus bi, that's kind of our main goal, is to have the real part on the left and the imaginary part on the right. You know, no matter which one's negative, which one's positive. All right, then we're gonna now want to learn how to multiply two complex numbers. So I guess even if it didn't say multiply in the directions here, I guess I would know we're multiplying because there's no, you know, there's no subtraction sign, there's no addition sign, there's no division sign between these two complex numbers. So as you've seen before, when two numbers or two variables or whatever it is, when they're sitting next to each other with no operation between them, it's just kind of understood that it's going to be multiplication. And this one, if you've never multiplied complex numbers before, the way you would guess to do it is exactly how you want to do it. I'm pretty much just going to multiply it out, or if you kind of remember FOIL, that acronym from algebra, it's like first, that's what F stands for, and then outer is what the O stands for, and then inner is the I, and then last is L. It's just, you know, which ones do I multiply? You're basically going to multiply the first term in the first parentheses by both terms in the second parentheses. So I'll do that. The 5 multiplied by the 6 makes 30. And then the 5 multiplied by the negative 7 makes negative 35. But you need the I attached because the 7i had an I. And then what do we have? And now we're going to, let's see, just to maybe show it with a different color here. Now we're going to focus on the second term in the first parentheses, 4i. And he's going to be multiplied by each of the terms in the second parentheses, 6 and negative 7i. So first, 4i times 6, that'll be 24i. Beautiful, okay. And then the 4 times the negative 7i will make negative 28. But this time it's an I times an I, so I'll have to write I squared. All right, I think it looks good. Just, I guess, be careful, because a lot of times I think grading exams and stuff like that, I've seen students, they miss the I squared. You know, they just write an I here. Or, I don't know, or they miss one of these i's, they just put the 35 or the 24 and not the I. So just be really careful of that and cognizant of what, I don't know, I guess how many i's there are multiplied together and what they'll create when they combine. So let's see, then we have some like terms, I think. These guys are like terms, they have an I attached. These two are not like terms yet, they will be. So if you remember, we wrote it at the very top in the very beginning of this lecture video. We said I squared was negative 1. So we can replace, anytime we see an I squared, which, you know, it'll only happen when we're multiplying or dividing complex numbers. But we're going to replace I squared with negative 1. All right, anywhere you see it, anytime you see it, it's free, you know, fair game to replace it. So kind of have two things going on right now. I'm just going to bring the 30 down. He doesn't know what to do yet. But these two were like terms we said. It's a negative 35i plus a 24i. That'll make negative 11i. So those are already combined. And then we said that this negative 28i squared, I want to replace the I squared with a negative 1. So literally where the I squared was, I'm just going to put a negative 1 in parentheses. So it's like this guy used to be an I squared, now it's a negative 1. But everything around him is the same, the negative 28 and all the terms before it. But let's see, now we can simplify that. Just going to bring the 30 down. This negative 11i, just bring it down. But now this last term, it's a negative 28 times a negative 1 that makes positive 28. And now all of a sudden that's a real number. So now I'm able to combine that with 30. 30 plus 28 makes 58. And then we have minus 11i. Now that looks more like a complex number that we're used to. Remember, we're supposed to have it, in the end, it's supposed to look like a plus bi. Although, I know I should have mentioned this earlier. If you might have been wondering this, but the plus, when you say a plus bi, I want my answer to look like a plus bi. It could be a minus too, so you could write a minus bi. I guess the thing is we more care about the real part being on the left and the imaginary on the right. Either of those is okay. I'm going to write or. But that's what it looks like here. It looks like real on the left and imaginary on the right. So that's how you know we did it right. And that's why I couldn't stop the problem at this stage here. Hopefully you can see the star that I'm drawing. Like, it looks like you might be done here. You're like, oh, I multiplied them out, so I'm all done. I'm sorry, I'm all done. But you couldn't leave the I squared there because, again, you want your answer to look like a plus bi, and that definitely does not look like a plus bi. Even if I were to combine these two middle terms, it still doesn't look like a plus bi. So you have more work to do when there's an I squared in your answer, because that's not, like we said, it's not simplified. Okay, so now we can move on to part 2a. Here they want us to multiply. And if you haven't seen something like this in a while, you're thinking, wait, multiply what? I mean, are you supposed to multiply this power in here? Well, if you remember, and if you don't, fine, then this is a good reminder that you can't distribute an exponent like that. So this is definitely not equal to, oops, what's that? What's going on with that guy? Not equal to negative 5 squared plus I squared. You cannot distribute an exponent like that. So we have to go back to kind of the basic definition of what it means to square something. This thing in parentheses, these two terms, negative 5 plus I to the second power, means I'm taking what's in the parentheses, negative 5 plus I, and I'm multiplying it by itself, negative 5 plus I. So that's really all it is. It's like I want two copies of this thing sitting next to each other, and I want to multiply them out. That's really what this means. So at this point, now that we've written it like that, it's more obvious, oh, okay, this is similar to the last one we did. I have to FOIL this out. So I'll do the first term times the first term. Negative 5 times negative 5 is positive 25. And then we do the outer times the outer. Negative 5 times I is negative 5i. And then we do the inner times the inner. I times negative 5 is negative 5i. And then the last times the last, I times I is an I squared. So that looks about right. And if you multiply a lot of these out, which you might do in your homework, you might see a pattern. It should be a real number, an I, and another I. So these two middle guys are going to be like terms. And then the last term should have an I squared. And of course, we'll replace the I squared with negative 1 like we did in the previous problem, or sorry, in the previous example, but, that'll be in a second. So we'll go, the first term is real. We'll just kind of carry it down, because right now it's not obvious if it has a like term. But the two middle terms are like terms. We have a negative 5i minus 5i. That'll be negative 10i, or minus 10i, however you want to say it. But remember that I squared is equal to negative 1, so we're just going to replace him with negative 1. And if it had a coefficient, like in the last problem, remember it was negative 28 I squared? The negative 28 stayed, but the I squared was replaced with negative 1. But this time there's nothing in front of the I squared, so it's just replaced outright. And now that that's just a real number, we can combine that with the first term, 25. So let's see, 25 and negative 1 makes 24. That's our real portion now. And then our imaginary portion is just coming from the negative 10i. And that looks about right. It's supposed to be a real number plus or minus an imaginary number. And that's what we have. So that's a good looking answer. All right, I think we're ready to move on to the next one. Let's see. And of course, when you're watching these videos, feel free to, if you didn't quite catch something or you didn't have time to write something down, of course, feel free to pause the video, rewind it, or fast forward it if I'm boring you to tears. Especially, if you already know something I'm saying. Yeah, please feel free. There's not going to be some little gem I throw in, or I don't know, like a secret thing that I throw in the middle of the video that you have to hear. That'd be kind of funny. Huh? Anyway, all right. So this one, part 2b here, it looks like there's obviously a complex number within the parentheses, But the guy in the front, 7i, doesn't look like a complex number. But remember, we talked about complex numbers might not have a real portion. So this guy is just purely imaginary. But he still counts as a complex number. So I know I feel like I messed that up. It looks too complicated, or too complicated. So I'm going to rewrite it and talk about what we're going to do. Imagine, sometimes if you have imaginary or complex numbers and you're not sure what to do, try to rewrite everything with x's instead of i's, and then usually your instinct is correct. So imagine this problem had x's instead of i's. It has 7x times 2 minus 9x. Well, what would you think to do to multiply that? Well, you would distribute, right? If you remember from algebra, distribute. Yeah, that's exactly what we're going to do. I'm going to distribute the 7i, multiply it by 2. Then I'll distribute the 7i and multiply it by 9i. So it'll be, let's see, 7i times 2 will be 14i. And then 7i times negative 9i, that's negative 63i squared, because that was an I times an I. And then by now we know that we're going to replace any I squareds we see with a negative 1. Let's see, I'm just going to rewrite it, except where the I squared was, I'll put a negative 1. All right, that makes it, let's see, 14i. He's just kind of hanging out, waiting to see what happens to the 63. But now it ends up being negative 63 times negative 1, so positive 63. And you know, that's a good looking answer, except we want to switch them because, remember, we always want it to be in the form a plus bi. We want the imaginary part on the right and the real part on the left. And this is kind of the opposite of what we want. So I'm just going to switch them, 63 and then 14i. There we go. And like I said, the line before the one we just wrote, the 14i plus 63i, that was technically correct. That's the correct answer. It's just, you know, it's not in the form we want. So it's, I don't know. I guess it's like if you're working and you write a report for your boss. You know, you might have written the report correctly. That's just, they might say, well, I kind of wanted it to be in this form, and I wanted you to write it in this, I don't know, font and this. It's kind of annoying, right? You're like, I did it, okay? I did it correctly, but they just want it to look a certain way, so I guess we got to do what we got to do, right? Anyway, don't go off on a tangent, right? Gotcha. All right, now we want to multiply these two together. This looks more like a previous example, not the one we just did, but the previous ones up here, where it was, you know, two terms, a plus bi and a plus bi. Well, this one's interesting because it has the same terms, you know, a 7 and a 7, and then a 3i and a 3i, but they have opposite signs in the middle, a minus and a plus. So these guys, just to point this out, because these will be important, oh well, coming up, they'll be important. And you might have seen this before. 7 minus 3i, 7 plus 3i are called, what are they called? Let's see, conjugates. Hopefully you can read my handwriting okay. All right, yeah, just conjugates. So that's, yeah, if you ever see two terms like these ones have, it's 7 and a 3i, but you see it written once with a minus and once with a plus, then that's their special relationship with each other. You know, they're not exactly the same, they just differ by the sign between them. One has a minus, one has a plus. And then after we multiply these out, I think we'll see why they have such a special relationship. So let's see, this one, we can use the FOIL method. We could do first times first is 7 times 7. Let's see, 49. That's the first times the first. And then we got the outer times the outer, 7, plus, and then times 3i would be plus 21i. That's the outer term. And then the inner is a negative 3i times a 7. That'll be negative 21i. Okay, and then the last times the last, that's the negative 3i times a positive 3i. That's negative 9i squared. If I can fit that in there. But then I notice, let's see, that the 21i, the outer and the inner terms, oops, I forgot to write those. Outer, inner, last. Okay. The outer and the inner add up to nothing. It's 21i, subtract 21i. They kind of cancel each other out, you know. Cancel. So they're gone. But let's see, I can keep carrying on with the 49. He's good. The two in the middle cancel each other out. Then I have the negative 9 from over here. But then remember that anytime you see an I squared, you want to replace it with negative 1. So I'm going to go, there was an I squared here, but I want to write a negative 1, because I know they're really the same thing. All right, and then let's see, I'll simplify that a little bit. We got 49, and then you have a negative 9 times a negative 1 makes positive 9. So you end up with a real number. 49 and 9 makes 58. So that's kind of important. That'll be important in a second. Let's see, we'll write that, I'm going to write that down. Multiplying, conjugate complex numbers results in a real number. And that's always true. I mean, this was just a specific example with 7 and 3i as our real and imaginary portions of the complex numbers, but if they were any other real or imaginary numbers, it would be true also. It would end up with something that didn't have any imaginary portion. All right, so this is where it actually is important. That's kind of why the division of complex numbers comes next. So there's not really a way to divide complex numbers outright. So it's kind of funny. I always feel like when they say these directions here, divide and express the result in standard form. Okay, divide should be in quotations because we're actually not going to be doing any dividing. As the directions say here, where I'm putting a little star, instead we're going to be multiplying the numerator and the denominator by the conjugate of the denominator. So obviously the denominator is 4 minus I. The conjugate of that would be 4 plus I. So let's see, I'm going to do that. 4 plus I, top and bottom. 4 plus I. All right, you know what? I'm just going to write this a little lower here, just so we have a better view of it. This problem started out 5 plus 4i over 4 minus I. Okay, I'm going to take that, and I'm multiplying it by the conjugate of the denominator, which means, like we said, it should have the same terms, 4 and I, but the opposite sign, so a plus. And you know, I think the idea is we want to make the denominator a real number, and we'll see why. It'll make the problem a lot better. Remember with a fraction, because you can think of this as a fraction, this guy, all you can do is do the same thing to the numerator and denominator. You can't just multiply the denominator by something and not the numerator, or vice versa. It has to be both or nothing. Okay, so we'll see what happens. But then that's a lot of work because we have to FOIL the numerator and FOIL the denominator. So I'm going to have to FOIL on the top and FOIL on the bottom. Ugh. So just be really careful when you do this. Let's see, we got the 5 times the 4 on the top makes 20. The outer terms would be 5 times I, which makes 5i. The inner terms are 4i times 4, which makes 16i. The last terms are 4i times I, which makes 4i squared. All right, so if you were careful, hopefully you got that as well. And then on the denominator, I'm going to FOIL it out as well. The first times the first is a 4 times a 4, that's 16. The outer times the outer is a 4 times an I, that's 4i. The inner times the inner is negative I times 4, which will make a negative 4i. And then the last times the last is a negative I times I, which makes negative I squared. All right, and then, you know, I think we did everything right. It's just now a matter of cleaning this up and making it look pretty. So dividing complex numbers is definitely the hardest operation we have. Because remember, we want our answer to look like a plus bi. And this definitely doesn't look like that. It's got some kind of real parts and imaginary parts and everything, but they're kind of running around in all different places. And I have a fraction. So obviously, when you have a plus bi, you don't want to see a big fraction bar. So we're going to have to work on that. But we'll just simplify the numerator and denominator as we've seen before. So for example, we have 5i and 16i. Those are like terms. I'm just going to go ahead and combine those. 5i plus 16i is 21i. All right, and then this 4i squared, we want to replace the I squared with negative 1. So let me see, just to maybe show what was replaced. I'll kind of highlight it with a different color. That I squared became a negative 1. And then we'll do almost the exact same thing in the denominator. I'm going to bring down this 16 just like we did to this 20. And then the middle terms, let's see, the 21, or sorry, oops, got the wrong thing. The 4i and the negative 4i cancel. So those just, yeah, those are gone altogether. But we should have actually expected that now that I think about it, right? Because we said that complex numbers, when you multiply conjugate complex numbers, which is what we did in the denominator, you should expect to have your outer and your inner terms cancel because there should be no imaginary numbers left. So the last thing to do in the denominator is to replace the I squared with negative 1. So it's now subtracting negative 1. And I think if we simplify this all the way down, it'll look pretty good. So let's see, I'm kind of running out of room here. I have 20 plus 21i. And then this term, the 4 times negative 1 makes negative 4. And then in the denominator, we just have a 16 minus negative 1, which, as you've seen before, makes 16 plus 1, which is 17. So we just have a nice real number in the denominator. In the numerator, there are some like terms. We have 20 and negative 4, those add up to 16. And then we have the 21i. So that, if I just left it like that, that would be a complex number, you know, that looks like a plus bi. I guess the only problem is we have this denominator of 17. But just to make it look really nice and look a lot more like the form we want, like they call it the standard form, a plus bi, all I have to do is separate it, 16 over 17 plus 21i over 17. So that kind of makes it look more like, separated. There's the real part, there's the imaginary part. That's all. So this, like we said, this is correct. It's as simplified as it gets, but we'd like it to see the real part it's with its own denominator and their imaginary part with its own denominator. I guess that's kind of the idea. All right. So now that we have, it's a complex process and a complex concept. I think now that we have the idea, then it'll go a little smoother as long as you're careful as you're foiling and all that. So that, like we did in the last one, we want to multiply. I don't know why I'm writing this out again. It's written out in the next, or the previous example. Oh well. Multiply numerator and denominator by the conjugate of the denominator. So in this example, I'm going to look at the denominator. I see it's a 2 plus I. So I think, okay, what's the conjugate of that? The conjugate should have the same terms, a 2 and an I, but the opposite sign. So I should see a minus. And whatever you do to the top, you have to do the bottom, and vice versa. I'm going to go ahead and just, like I said, just start foiling it out and see how it goes. So in the numerator, I'm going to do FOIL, and then the same thing in the denominator, but I'll focus on the numerator first. The first times the first makes a 4. The outer times the outer makes negative 2i. The inner times the inner makes a 6i. The last times the last makes negative 3i squared. So going a little faster now, just because I feel like we've done this quite a few times. And then in the denominator, we'll do FOIL as well. FOIL, okay. First times first is 4. Outer times outer is negative 2i. Inner times inner is positive 2i. And the last times the last is a negative I squared. So now to simplify, our job is to, let's see, combine any like terms. So this negative 2i and 6i, those are like terms. And this negative 2i and 2i cancel. So they'll just disappear. And then we'll replace any I squareds with negative 1. So these I squareds that I'm coloring in orange, they'll become negative 1s. So this 4 in the numerator just comes down, this guy right here. And then this, the negative 2i and the 6i add up to 4i. And then after that we add a negative 3 times I squared, but I'm going to replace the I squared with negative 1, of course, like we mentioned. All right, and then something similar is happening in the denominator. It's just that the outer and the inner terms, the two middle ones, cancel each other out. So now we're just left with this 4. And then this negative I squared becomes a negative, or sorry, subtracting I squared becomes subtracting negative 1. So just don't lose this subtraction sign, I guess. That guy should stay. I think there's so many little steps to this, it's easy to make a little mistake. So just keep that in mind. I think if you get any of these wrong and I don't know, don't feel guilty. It's not like you did it's not like you don't know what you're doing, I guess is what I'm trying to say. You know what you're doing, it's just, if there's a lot of tedious steps to a process, it's just easy to make a mistake. All right, so let's see. I'm just going to rewrite the numerator, 4 plus 4i, but then we had a negative 3 times a negative 1. That makes positive 3. And then the denominator looks like 4 minus negative 1, which actually makes 4 plus 1, which is 5. So it looks like this is going similar to the last one. And then in the numerator, we have a few like terms now. The 4 and the 3 makes 7. And then there's a 4i. And that's all over 5. Okay, that looks good. So I'm going to go ahead and just rewrite it like we did before. I'm going to give the real portion its own denominator of 5, so 7 over 5, and then the imaginary portion its own denominator of 5, 4i over 5. And that looks good. That's more the standard form we want, a plus bi. Okay, I think that looks good. All right, so that's how you divide. And it's not amazing, it's not exciting, but it's okay. All right, so I think we're almost done here. These last couple problems are problems 4, A, B, and C. They want us to just kind of perform these random operations. They're kind of giving us all these different crazy things. But they're it's mostly review of algebra, I think, or if you learned about square roots before. But the main thing is, in example 4, all these ones down here, example 4, all these 6 little examples, we want to change imaginary numbers to something in terms of I. In terms of I, which the way to do that is you just replace the negative that's inside the root, because remember that's how you know it's or an imaginary number. So these all should have a negative inside the root. Replace the negative in the root with an I outside the root. Okay, so if you just remember that, you should be okay for these problems. Once you do that, everything should be all review, you know, whatever other properties you have to use, it's review from previous classes. So let's see, for example, and that, you know, that sounds like, I don't know, like witchcraft. Can you do that? Is that okay to just all of a sudden replace a negative with a blah, blah, blah? Okay, so maybe in the first example, we can show why. So if you remember from algebra, if I have something like the square root of negative 27, I'm free to split it up into two numbers, like negative 27 is equal to 27 times negative 1. And if you find two numbers that multiply to create the number that's inside the root, you're free to just split it up into two different numbers. So I'm going to go ahead and do that. And same thing for this guy, negative 48. I could write that as 48 in its own root, and then the negative 1 in its own root. And they're being multiplied, the 27 and the negative 1, the 48 and the negative 1. And I only do that because I would like to see the imaginary number portion kind of separated from the real portion. Because I want to simplify the 27 and the 48 without worrying about the imaginary stuff. So I'm just going to, for now, I'm going to leave the 27. But now that I see that I have a square root of negative 1, I remember that that was the definition of I. And same thing with the 48. The 48's good, but the square root of negative 1 is just I. So really what happened if I skipped the middle part, the middle step, I took a negative that was in the root and I just threw an I at the end for both of these terms, you know? So that way, I mean, if you just kind of memorize that process, then you can kind of skip this middle step if you want from now on. Just go from here to here. I'm just going to get rid of the negative that's inside the root and put an I at the end. Bada bing, bada boom. And I don't want to mislead anyone. Let's see. I don't want that. I want this. This I is not inside the root. It kind of looked like it was. Yeah. All right. But now, from algebra, you're not able to combine roots unless they have the exact same number inside the root. So right now, these are not like terms. There's a 27 inside one root. There's a 48 inside the other. But maybe I can simplify both until they have they're like terms. So I just think, what can divide into 27 that has a square root? That would be 9. So I'm going to split it up into 9 times 3. And then 48, what divides into that has a square root? That one's a little tougher, but 16 actually goes into 48 3 times. And 16 has a square root. Let's see, 9 square root is 3. So I'll write 3 root 3i plus, let's see, 16 square root is 4. So I'll write 4 times the square root of 3i. All right, and now they are actually like terms. It looks really complicated, but I guess you're thinking, this is like your variable here, the root 3i. Those are the same thing. So at this point, it doesn't look like it, but it's kind of like we have, 3x plus 4x. I guess, thinking of this whole root 3i as your variable. So that, if you were to add 3x and 4x, you get 7x, right? So I'm going to go ahead and try to, seems weird, but I'm going to go ahead and do that. So we got 3 and 4 makes 7, but just instead of an x, we have root 3i. So that looks weird, but that's our answer. So okay, now that we have that idea, I think we can get going on the next one. So this, I'm going to take the negative away from the root like we did before. Just write square root of 64, and then stick an I at the end. And same thing with the next guy. There's a subtraction sign, and then there's a negative inside the root with 25. I'm going to get rid of the negative and put an I at the end instead. And now, actually, this one's a little easier because I don't have to split this root up. 64 has a square root outright. It's 8. As does 25. It's just 5. So now, okay, now we see. It's 8i and 5i subtracted make 3i. There we go. So actually, that one was a little easier, huh? So, you know, if the first one we did the previous one we did with the negative 27 and the negative 48 in the root, if that was pretty difficult, then I think what I would do is go back and review a little bit of roots. Because you'll see a lot of it in the homework of this section, and then we might see roots again later in this class. I believe we do. So just be careful. And in this example we're looking at here, it looks like we have two terms. It's -2 and then root -3. I'm going to do what we did before and get rid of the negative, put an I at the end instead. And now this becomes a lot like a previous one we saw. We have two terms inside with a square outside. We have to actually write this twice and then FOIL it out. Okay. So what do we have here? -2 times -2 is 4. And then -2 times root 3i. Those are not like terms, so we can't combine them. You know, you can't say 2 times 3 is 6, because the 2 is outside the root, the 3 is inside. The best I can do is write them next to each other. And then the same thing with the inner guys. It's a root 3 times a -2, that makes -2 root 3i. And then the last times the last, okay, that's, let's see. Let's get a good color here. Root 3i times root 3i. Well, the 3's are both inside the root, so they can actually be multiplied together. Root 3 times root 3 makes root 9. And then there's an I times an I, which will make an I squared. All right, I think we can combine some like terms. These guys are like terms. We have -2 root 3i and another -2. It's like, you know, it's like we had minus 2x minus 2x. That makes -4x, except the x is a root 3i. And the very last term, the square root of 9 is 3. And we know by now that I squared should be replaced with -1. So this becomes 4 minus 4 root 3i, and then minus 3, because that last term became a -3. Now we have some like terms. 4 and -3 make 1. And then I'll just write the minus 4 root 3i. And technically this isn't the right form, a plus bi, or a minus bi. It's just that the b portion, b is complicated. It's 4 minus 3i. That's kind of, you know, it's kind of wild, kind of crazy. In a good way though, right? Of course. All math is crazy in a good way. No, just kidding. I don't know about that. Okay, and then this guy's similar. Let's see. We might be able to go faster on this one. Let's see. Sorry, sometimes this computer, it kind of overheats when I've got a long video going on. Sorry about that. So I hope you don't hear sounds like a freaking vacuum cleaner or something. Okay, so the square means I'm going to write this thing twice. I do not like all these negatives, but, well, we'll get rid of one of the negatives, the one that's inside the root. Remember, we're supposed to write, I'm going to get rid of the negative inside the root, just write a root 7 and put an I instead. So I'm going to make it a little better. My root 7 and then I. Okay, now we're going to FOIL. So I have first times first, -3 times -3 is 9. Outer times outer, negative times a negative is a positive, 3 root 7i. Same with the inner. Oh wait, why'd I put a plus there? That's a minus. Hello. Silly. Negative times a negative is a positive. And then you could write root 7 and then 3, but usually you write the real part in the front and then the root part. 3 root 7i. Okay, then the last times the last is a negative times a negative again. This time it's a root 7 times a root 7, which makes a root 49. And it's an I times an I, so I'll write I squared. All right, so it's looking similar to the last one so far. 9, and then we'll combine like terms here. Like we said before, think of this middle guy as like a 3x plus 3x, you know? Even though it's a root 7i as your x. But that would make 6 of whatever you're trying to add, and we're trying to add 7i, or root 7i's. And then the square root of 49 is just 7, and I squared is -1. Looks like we're getting close to the end here. 9 plus 6 root 7i, and this makes a -7. Okay, looks good, so we'll go. The 9 and the 7 are like terms now, they make 2, plus this other term, 6 root 7i. There we go, all right. I think we got it. All right, I think now we're on to the last example here. This one I think it's more simplifying, so this one probably should be a little easier. Let's see, we'll go ahead, do what we've been doing for the last couple examples. Whenever I see a negative inside a root, I'm just going to get rid of it, so I'll just write the square root of 12, and then I'll just stick an I at the end. And that's all over 2, okay. And then let's see, the square root of 12 simplifies because something divides into 12 that has a square root. That would be 4. So I'm kind of going to think of this as square root of 4 times square root of 3. Let me see, I'm going to go ahead and rewrite that. -14 plus the square root of 4 times the square root of 3i. That's all over 2. All right, that makes -14. And then the square root of 4 is 2. So I'm just going to replace that square root of 4 with 2. There is no square root of 3, so he'll have to stay as is. and then the I all over 2. And at this point, this is kind of back where, remember we had one big denominator? We want to split this into 2 fractions at this point to simplify. Split into 2 fractions to simplify. Because, you know, this is a correct answer. It looks pretty simple, but there's a little bit more we can simplify. You know, because if it's been a while since you've seen algebra, you're thinking maybe these 2's cancel. And they kind of will, but you also actually have to involve this 14. He'd have to cancel along with everybody. You don't want to leave him out, you know. You feel bad. You're going to make him sad. So just so I don't try to cancel the wrong things, I'm going to rewrite it. Negative 14 over 2, give him his own denominator, and then 2 root 3 I over 2. That way I know kind of what to cancel and what's okay to cancel. So this guy, 2 can go into 14 7 times, so that'll become a negative 7, just this portion here. Plus, and these 2's just cancel, the ones that are next to and above the square root of 3. So it looks like we end up with negative 7 plus root 3i. That's it. So these last examples are, you know, they're okay. They're not that exciting, but they're, you know, they're important. And I think these are important because I don't know if you kind of remember, if you've seen the quadratic formula before, which, you know, you might not have, you might have, but a lot of times when you use the quadratic formula, you get imaginary answers, and they might end up looking something like this. I think if you kind of remember that, they have a very similar look. And I think students have a hard time remembering how to simplify them. So this is kind of practice on that. All right, so we'll do pretty much the same thing. We're going to rewrite the negative 8. I'm going to rewrite the square root of negative 32 as just the square root of 32 with the I attached. And then over 24. Let's see, now I'm going to try to simplify the square root of negative 32. Okay, I think what's the biggest number that divides into 32 that has a square root? That would be 16. I'm going to rewrite 32 as 16 times 2. Is that right? Wait, yeah. Times I. So yeah, hopefully that makes sense. We're going to rewrite, basically 32 became 16 times 2. And you're free to split up a square root over multiplication like that. And that's over 24. Okay, let's see. Negative 8 plus. And the whole point of that was because the square root of 16 is 4. That way, it's kind of like part of the 32 can escape the root. But that 2 will be stuck in there forever. And now we'll do the very last step like we did in the last one. We're going to split it up into 2 fractions. I'll give the negative 8 his own denominator of 24. And then the 4, root 2i, his own denominator of 24. And then I'll just reduce as if they're regular fractions. This guy reduces to negative 1/3. And this reduces to root 2 over 6i. There we go. I think that looks good. And I think that kind of covers everything we need to know here in this section. So hopefully that all made sense. And if not, please let me know or go review it's probably just a matter of reviewing square roots because that's a tough subject. All right, so I'll see you in the next video. Thanks for listening.